Hello my dears, how are you all? So I think in the last class we did some problems, important problems regarding the concept of slip and all, right? Slip and all, I mean rotor frequency. We derived the expression for rotor current frequency and we did some important problems regarding that. And in today's class also we will continue with some more problems and we will learn new sessions, okay? Later on we will learn new sessions. So please write a question. Please write a question, my dears. A voltmeter gives 120 oscillations. 120 oscillations per minute. When connected to the rotor of an connected to the rotor of an induction motor, full stop. The frequency is 50 hertz. The frequency is 50 hertz. Slip of motor is, then the slip of motor is. Read the question carefully. These type of questions you may expect in your examination. No? Not very lengthy, but you have to think a little in order to get the answer. Okay. A voltmeter gives 120 oscillations per minute when connected to the rotor of an induction motor. That means the rotor frequency is directly given by Fr is equal to what? 120 oscillations per minute, right? Per minute. But frequency will be per second value, right? So in order to convert the minute quantity into second, divided by 60, correct? So it will be what? 2 hertz. So the rotor frequency is directly given by 2 hertz, okay? The frequency is 50 hertz, that means the supply frequency is nothing but, my dears, 50 hertz, right? 50 hertz. Then the slip of the rotor is simple. What is the equation for? Fr will be S into Fs, correct? We have the relation, right? So simply substitute S is equal to what? Fr by Fs, which is nothing but 2 by 50, okay? Better you have to convert it to percentage slip, right? Percentage slip. Percentage S will be equal to 100. Calculation will be very easy, that's why. So it will be 2. So it will be equal to 4%. And slip S will be equal to 4 by 100 or simply 0.0. That is the answer, boss. See how easy the question is. But you have to think a little, right? Think. Then only you can answer, right? Then only you can answer. Did you get the answer? So 4% is the answer, okay? Next question. So this is very easy question, but you have to think, right? So can I remove this? Next question. In the slip ring induction motor, the frequency of rotor current can be measured with a dash. Options: MI, instruments, and B, DC milli voltmeter and this is MC, moving coil, DC milli voltmeter. Wattmeter. How can we measure? It's very important question, my dears. Very important question. If you know the concept, then the answer will be very easy. See, in the slip ring induction motor, we know there are two types of induction motors are there. And first one is squirrel cage, in which we can't connect anything to the rotor circuit. That means we can't control the torque of that motor. That's why its rotor will be permanently short circuited. That is the nature of squirrel cage. But in the case of slip ring induction motor, there is a provision for connecting some external resistance to the rotor. Either it may be in star, definitely it may be in star, no. So we can connect some external resistance. So in such a slip ring induction motor, we connected some device in order to measure the frequency of rotor. Normally, the rotor frequency will be, the rotor frequency FR will be, this is nothing but Fs in the Fs. It is very low, right? It is nearly very low frequency, right? It is very low frequency, say 2 Hertz and all, right? Say 2 Hertz and all. So in order to, what is the meaning of 2 Hertz means? Per second there are 2 oscillations, right? Per second there are 2 oscillations. So if you are using an MI instrument, what happens means, the MI instrument has a nature that it will be measure the square of the what? That is theta proportional to I square, right? In theta proportional to I square. For both negative and positive value, it will square and there will be uniform what? Scale of that MI instrument. There will be scale will be uniform, that is only towards the positive side, right? Only towards the positive side. So by using that MI type instrument, we can't measure the frequency because it won't deflect, right? It won't deflect. It is uniform deflection will be there, so we can't measure that. And of course this we can't measure that. Next one is what? Wattmeter. Wattmeter is a device used for measure the power, right? Voltage into current into angle between voltage and current, it will measure. Cosine of the angle between voltage and current, it will measure. We will directly give the value of instantaneous power, right? Sorry, average power. We will give the value of average power. So these wattmeter cannot be used to measure the frequency. Next, see this one, DC milli voltmeter, EMC type. What is the nature of moving coil instrument? Moving coil instrument can be used only in DC circuit because it is supposed that it's a scale, that means the deflecting angle of this is for MI, and for MC type instrument the deflection angle theta will be directly proportional to I only. Theta proportional to I only. Okay, these things you will definitely study later when we are going to deal with what measurement systems. We will definitely learn this, but I think you have an idea, right? I think you have an idea. So in moving coil instrument, the deflection angle theta will be directly proportional to what, my dears? I. That means if this is the supply, of course in rotor circuit AC will be generated, right? So for positive half cycle, the deflection will be in positive direction, right? This will, the pointer will be like here. Suppose the pointer will be like here. And for negative half cycle, the deflection angle theta will be directly proportional to I know, it will be minus I know. So the deflection angle will be in reverse direction. That means the point will come here. So for one half cycle, it will be like this and it will be like this for one complete half cycle. If the frequency is very high, means due to the inertia of the meter, due to the inertia of the needle, we can't say that it will be moved here and here. But if you apply 50 Hertz means, if you apply 50 Hertz supplied to this system or moving coil instrument means 20 millisecond is just needed to complete one cycle. It's very small, right? That means in 10 millisecond it will be in positive direction, in another 10 millisecond it will be negative direction. It's very small value. So due to the damping or due to the inertia of the deflection system, we can't see the positive and negative movement of the needle because that much high frequency is there. So at that time, that means if you send an AC signal of high frequency to the moving coil instrument, the coil needle, I mean the needle will be simply idle. It can't go there, it can't go in backward. It can't go forward, it can't go backward, because it will be simply in idle position. Because that much frequency applied, you not allow this needle to forward and backward, because that much high speed you are applying the signal. But if you lower the frequency to very small value, say 2 hertz, the needle get enough time to move forward, the needle get enough time to move backward, right? The needle gets sufficient time for its fluctuation by overcoming its inertia. It will get sufficient time. So if you send some 2 hertz signal to the DC Milli Voltmeter, because in rotor circuit there will be a small voltage, right? Small voltage will be generated, right? So we can simply use Milli Voltmeter, that's okay. And 2 hertz, the meaning of 2 hertz means the rotor induced current will have a very low frequency. So the moving coil can move for some time, can move like this, for some time it can move like this. That means 2 hertz means a full signal can be sent in how much time? 1/2 seconds, that is 0.5 second. By using 0.5 second, it's not that much small value, right? So we can easily measure the frequency. 1, 2, 1, 2. You can easily measure that. So DC Milli Voltmeter, that to moving coil type DC Milli Voltmeter is the correct instrument which can be used to measure the rotor frequency. Did you get the idea, my dears? So only thing you have to know, for Mi, theta will be I square, so the deflection will be uniform. That we don't want. We want frequency, no? Then we can say that, okay, 1, okay, 2. How many time? 1, 2. I mean, in what time it will become forward and backward, that is the frequency, right? Come forward and backward. In what time? That is the frequency. Correct? Correct. Then 1 by time will be give the frequency. Okay. So I think the explanation is enough. So MC type instrument is sufficient for measuring low frequencies. So in interview you may ask a question like this. For measuring low frequencies, normally moving iron instrument is used in AC and a moving coil instrument is used in DC. But can you use moving coil instrument in AC also? Yes, it can be used, but the frequency should be very low, say 1 hertz, 2 hertz, 0.5 hertz, like that. Then you can use that instrument. You will get the value, no issue. You will get the value. So that also a type of explanation. So the explanation is sufficient, right? If you still have any doubt, you can comment in the comment section. Okay, I will explain. Okay, I will explain once more. Okay, my dears. Next, we are going to another important question. The frequency of rotor current at standstill is. How can we do, my dears? We have general equation for Fr is equal to S into F. So at a standstill, what is the value of S? Will be equal to 1. In doubt? Slip is nothing but Ns minus N divided by Ns. So at a standstill means the rotor speed will be 0. So simply Ns by Ns, which is equal to 1. Okay. So at a standstill condition, S is equal to 1, my dears, 1. So Fr will be equal to simply F. Rotor frequency will be simply equal to the supply frequency. rotor frequency will be simply equal to the supply frequency. Okay. Okay. So that's all about the question. Did you get my ideas? Did you get my points? Is there any doubt you can ask? Is there any doubts? Is there any doubt you can ask? Okay. Next. Stator induced EMF. See, it's very important. These sessions are very important, my dears. Here the heart of the induction motor lies. Okay. See, there are stator, you know as this is the stator. There will be of course some stator winding side. So there will be some stator winding, and inside that there is rotor. There is of course some rotor winding. So in the stator winding you are going to give 3-phase supply, correct? Stator winding you are going to give 3-phase supply. Since it is a winding and we are giving an alternating voltage to the stator supply, definitely there is a chance of producing a back EMF from the winding side, right? Because whenever we are giving an AC to the winding which is coiled in structure, that's also called winding, right? We are giving some supply to the winding. Due to the varying magnetic field, there is a chance of self-induced EMF in the winding itself. That is called the back EMF. So we can say that the induced EMF in stator windings will be equal to, say I represent like E1 phase. Induced EMF per phase, it is E1 phase, will be equal to 4.44 into F into phi into Fs, that is Fs into phi into T phase into kW. That much volts. This is a very important relation, I guess. Very important relation. This is the back EMF equation. See, in the transformer also, these induction machines can be considered as a rotating transformer. It's a one word question. The 3-phase induction machine or simple induction machine can be considered as a 3-phase rotating transformer. At a standstill condition, same procedure, same behavior as that of the transformer, the machine also can exhibit. That means the machine is equal to the transformer itself. We are giving in transformer, see, there are primary and secondary winding. Here it is stator and rotor bus. We are giving supply to the primary winding in transformer. We are giving supply to the stator winding in the motor. Clear? We are taking output from the secondary winding of the transformer. We are giving taking output from the rotor of the induction motor bus. Only that is the difference. Clear? So this induction motor can be considered as a rotating transformer. Induction machine are considered or equivalent to, that is the correct word, right? Equivalent to a rotating transformer. Yes, very important. This is very important. You have to note it. So the induced EMF in the stator winding is same as that of the transformer induced EMF in the primary side, that is equal to E1 phase, which will be equal to 4.44 into Fs. Fs is nothing but the supply frequency, phi is nothing but the flux induced, and T phase is nothing but turn per phase. T phase is nothing but, my dear, turn per phase, and Kw is nothing but winding factor. Winding factor. I mean, apart from the transformer, the winding factor, here we are introducing a winding factor here in induction machine. All the machines are winded in some manner, right? Wound in some manner, right? Wound in some manner. So we have to consider for a factor which is linked with the winding, that is called the winding factor. And winding factor is nothing but, my dears, Kp into Kd. Kp into Kd, where Kp is the pitch factor and Kd is the distribution factor. Kp is the pitch factor and Kd is the distribution factor. These terms now, Kp, Kd and winding factor, we will definitely study it in alternators. There it can be clearly we can study there. Clearly we can study there. As of now, you will be in problems in relating transformer. You will be directly give the value of K by D, that is winding factor. That means a factor should be included in the EMF equation in order to compensate for winding bus. That you just know that. You just take an idea of this only. Due to the winding imperfection, say some we can say in like that, due to some winding imperfection, a factor should be included in the EMF equation. That factor is nothing but winding factor, and its value is equal to Kp into Kd. It will be equal to pitch factor into distribution factor. The product of pitch factor into distribution factor will be winding factor. What is this pitch factor and what is this distribution factor now? We will learn in the alternator section. That will be very easy then. Okay. Suppose I took that now, it will be very complicated, right? Because you are not at all having an idea of windings and all. What is pitch and distribution? How can be the winding arranged? So when we are dealing with alternator, it will be very easy for us. Okay, easy for us. So this is the induced EMF equation. Only you have to remember this equation, my dears. E1 phase will be equal to 4.5 into Fs into 5 into T phase into Kw. This is the induced EMF in the stator winding. Next you have to see rotor induced EMF. Rotor induced EMF at standstill. Rotor induced EMF at standstill. So let be E2 phase will be the rotor induced EMF at stand phase, which is nothing but, my dears, there is a relation So this is the rotor induced EMF in the at a standstill condition. That means in the rotor side also there is an induced EMF, right? Similar to the transformer. You compared this with the transformer, then only it will be very easy. Otherwise it will be very difficult and very you can't able to imagine. Suppose you imagine for transformer, then it will be very easy, my guess. Then it will be very easy. Okay. So we have a relation in transformer as V2 by V1 equal to N2 by N1 bus. Instead of N2, it will be T2. T2 turns per phase, right? Turns per phase, because it is a 3-phase winding, right? So turns per phase will be the correct value. So E2 phase by E1 phase will be equal to T2 phase by T1 phase. So from that, E2 phase will be equal to E1 phase into T2 phase by T1 phase plus. So this is a rotor induced EMF at a standstill condition. Then rotor induced EMF at loaded or running condition. Rotor induced EMF at loaded or running condition. So what will be the difference? What will be the difference? See, say it will be E2 phase dash. Rotor induced means simply E2 phase. Dash means it is under running or loaded condition. It will be equal to, my dears, 4.44 into Fr into 5 into T2 phase into kWr. See, what is the difference compared to the EMF equation in stator? the frequency is Fr, right? Because the rotor is rotating, so we have to consider for rotor frequency, right? That Fr is nothing but, my dears, it is nothing but S into Fs, correct? S into Fs. So we can write like E2 dash phase will be equal to 4.44 into S F into S Lect, correct? Or Fs into S into phi into T2 phase. It is a winding factor of rotor, correct? Winding factor of rotor. Or I can say that, my dears, E2 dash phase will be equal to, what is this 4.44 into Fs into phi into T2 phase? What is that? It is nothing but into kWr. This only small change will be there, because we already told you that the winding will be same as that of the stator and rotor. Stator and rotor will be almost in same winding structure, so the winding factor will be similar there. But we just for the understanding purpose, simply we kWr means winding factor in rotor, that also equal to the winding factor in stator. So it will be equal to, my dears, 4.4 into Fs into phi into T2 phase is nothing but E1 phase, correct? Sorry, E2 phase, correct? That is the for E1 phase. E2 phase, no? E2 phase is nothing but 4.44 into Fs into phi into T2 phase is nothing but what? What? It is the E2 phase, correct? It is the E2 phase into the difference term is that, what is that? Yes, correct? So E2 dash phase will be equal to E2 phase into S. E2 phase into S, correct? E2 dash phase will be equal to E2 phase into S. That is the only relation we can develop from here. Okay, so by using these equations, we have to derive or we have to draw the equivalent circuit of the induction motor. That is very, very important. Okay. Please clearly note this, otherwise it will be very difficult. It will be very, very difficult. It will be very, very difficult. So next we have to go for equivalent circuit. Next we have to go for equivalent circuit, my dears. Equivalent circuit. So we have to go for first stator side. Stator equivalent circuit. Stator equivalent circuit. See. This is the equivalent circuit of the stator side. Can you found any similarity with the transformer? It is exactly transformer no load equivalent circuit, right? It is similar to transformer no load equivalent circuit, correct? It is equal to transformer no load equivalent circuit because it is similar to transformer, right? It is similar to transformer. So this is the stator what equivalent circuit. Next you have to see for rotor side. Next you have to go for rotor side. So rotor at standstill. At standstill means, my dear, S will be equal to what? 1. Correct? S will be equal to what? 1. So see, so simply E2 or E2 phase, both are same, E2 or E2 phase. So this is the equivalent circuit in what? Standstill condition. Next, rotor at a running condition. running condition means, my dear, S less than 1, correct? S less than 1. So it will be equal to so this will be the equivalent circuit and running condition. In both the cases, you may notice one thing, that the rotor side is short circuited. Why? Because we know that both in squirrel cage as well as in slip ring induction motor, the rotor side should be closer circuit, right? In slip ring induction motor, there is an additional resistance, but that also finally what? Short circuited. That also finally short circuited. And in squirrel cage induction motor, the windings can be short circuited by using two end rings, no? That also short circuited. That's why the rotor side is short circuited simply. And see, at a standstill condition, S is equal to 1 means there is an induced EMF E2 in the rotor side, and R2 is the rotor resistance, Jx2 is the rotor reactance, and this short circuit. And here at running condition means S less than 1, and the rotor induced EMF will be S times the induced EMF in the rotor, correct? We derived that equation now. E2 dash will be equal to S into E2, correct? S into E2. So SE2 is equal to this I2 and J into X2 into S, because I will tell you one thing. If you introducing the concept of slip, it will affect in the reactor. It will affect the reactor. Why? Because I will tell you, we have the relation omega equal to what? 2 pi into F, correct? Or omega R equal to what, my dear? 2 pi into Fr, correct? 2 pi into Fr. This omega is related to definitely the rotor, right? Rotor. Omega is rotor angular velocity, which will be equal to 2 pi into Fr. It can be treated like 2 pi into S into F, correct? So it can be treated like S into 2 pi into Fs is nothing but omega S. So this is omega S, correct? Omega S. Omega S. So omega R will be equal to S times omega S, correct? S times omega S. So if you introduce a slip, where it will be affected? It will be affected at the reactance, because inductive reactance is nothing but inductive reactance X is nothing but 2 pi F, correct? L omega, right? X is equal to nothing but L omega, that L into 2 pi into F, correct? If you go for this rotor, then it will be Fr. So simply L into 2 pi into S into Fs. So it will be simply 2 pi into S into Fs. So L into 2 pi into Fs is nothing but, my dears, omega S into S, correct? So XR will be these times L omega is normal reactance into S, correct? So if you introduce slip, it will directly affect what? It will affect the rotor reactance, not the resistance, because there is no terms in the resistance, right, associated with the frequency. So in the rotor reactance is the only term which affected by the frequency change. So XR is equal to nothing but L into omega R, right? L into omega R. So that is L into 2 pi into Fr. L into 2 pi into Fr is nothing but S into Fs, right? So L into 2 pi into Fs is nothing but omega S. Yeah, 2 pi into Fs is nothing but omega S. So it will be L into omega S into S, correct? So L into omega S is simply X, correct? Simply X. So XR will be equal to, at the running condition, it will be equal to into S times at the, when it is in running condition, it will be equal to S times the reactance at a standstill condition. This L omega S is nothing but standstill condition, right? Standstill condition. Because omega is the frequency. We already learned that at a standstill condition, the rotor frequency is same as that of the stator frequency. That means the rotor reactance value will be same as that of the frequency of the supply voltage. That means rotor reactance frequency will be equal to same as the supply frequency, right? So it will be L into omega s, that is the standstill condition, into S at the running condition. It is the running condition. So the terms which is going to change when it is in running condition is the only reactance Jx2 into S. That is the explanation. Because in the rotor side only R2 and Jx2 was. R2 and Jx2. In the transformer also in the secondary winding only R2 and Jx2, right? Similar manner, here also it is simply R2 and Jx2, my dears. R2 and Jx2. Is it clear, my dears? Is it clear? Is it clear? Okay. So this is the equivalent circuit, and I am going to apply KVL here. I am going to apply KVL here. So let be figure 1 and let be figure 2. Okay. So apply KVL in figure 2. What I get? Apply KVL in figure 2. What I get, my dears? It will be equal to S into E2 equal to, my dears, it is I2 into R2 plus I2 into J X2 into S, correct? Simply you applied the KVL equation. So divide both sides with S. What I get? SC2 divided by S equal to I2 R2 by S plus I2 into Jx2 into S by S, correct? I divided both sides with S, my dears, bus. S and S cancel here, S and S cancel here. So result will be E2 will be equal to I2 into R2 by S plus I2 into Jx2, or simply I2 into R2 by S plus J into X2. It be equal to E2. This is our area of concern. This is our area of interest. This equation is our area of interest. So by using this equation, I am going to draw a new equivalent circuit in the secondary side, which is nothing but, my dears, listen very carefully. There is no change in that, but here it will be R2 by X and here will be simply Jx2 and it will be I2 and it will be E2. It will be E2. Bus. This is the equivalent circuit of what? Rotor side. Rotor side under running condition. This is the equivalent circuit of rotor side under running. Please note this. Please note this. Please note this. Please note this, my dears. Okay, did you note this? Did you note this? Can I rub? Can I rub? Next, approximate equivalent circuit. Referred to stator side. Approximate equivalent circuit referred to stator side. Okay. See, what I am going to do is, So this is the approximate equivalent circuit at stator side, referred to stator, side. Okay, I1, I2, I0 can be split up into IW and IM, I2 dash. Why I put I dash here? Because we already learned in transformer that I converted. I am going to refer to stator side, mean I have to take the rotor parameter to the stator side. Similar to I have to take secondary parameter to the primary side in the transformer. The same manner I am going to take the rotor parameter to the stator side. That is why R2 dash by S. Instead of R2, it will be R2 dash by S, and instead of X2, it will be simply J into X2 dash plus, and instead of I2, it will be equal to I2 dash. And one more thing you have to note that here the core loss in stator is very less or negligible. So the equivalent circuit become see this R omega is nothing but a small amount of drop heat will be generated in the core due to the core loss, not due to the copper loss. Copper loss will be due to this R1, but core loss will be a small amount of core loss in the form of heat will be generated due to this RW. That is very negligible compared to this R1 and R2 etc. So that can be neglected. So the equivalent circuit will become a new form like this will be the format. This will be the equivalent circuit then. Nothing but we simply removed this, and the remaining will be simply marked as X0 because there is no IW. The whole I0 will be termed as the IM. So it will be the final equivalent circuit of the induction motor referred to what, my dears? Referred to primary side or referred to the stator side. Bus. Draw it. Okay, can I remove this? Next, very important session, power flow diagram in induction motor. Power flow diagram in induction motor, very important ideas. So stator input power minus stator core and copper loss will be the rotor input or air gap power represented by PG, and again minus rotor copper loss will be the mechanical power developed, PMD, and again minus frictional and windage loss will give you the value of shaft power or useful power. So this is the power flow diagram of a 3-phase induction motor or simply induction machine. I will explain. We have some stator input power in our hand, right? We are giving to the stator side, we are giving to the stator 3-phase winding. So definitely stator is made up of laminations and there will be some windings. So in stator there will be stator core and copper losses. The stator core loss will be there, plus due to the stator winding resistance there will be some stator copper losses. So from that power, that is the stator input power minus the stator core loss and copper loss will give you the value of rotor input power or air gap power. That means stator side you gave a power, there are some losses in the stator side, and after that there will be some power which is available at the air gap. That is nothing to the rotor input power, correct? Stator side and rotor side, see, this is stator and this is rotor. We gave some supply to stator, there are some losses, and the remaining power will be available here. That is nothing but the rotor input power, or simply we can say that is the air gap power made as air gap power. See, that is PG. PG is nothing but air gap power. And again minus that air gap power minus. So not the whole power can be converted into the rotation in the rotor, correct? Because we have to overcome the rotor resistance is there, right? We have to overcome the rotor resistance. For that there will be some rotor resistance loss. So that rotor copper loss will be there. So from the power that is injected to the rotor side, there will be some rotor copper loss, and the remaining power will be the mechanical power developed inside the rotor. That means we gave power to the rotor, and that power will be definitely due to that there will be some current in the rotor side. Due to that current there will be some losses in the rotor conductor, right? That is called the rotor copper loss. And minus that rotor copper loss, that is rotor input power minus that rotor copper loss in the conductor will be equal to the generated power inside the rotor shaft, correct? Inside the rotor. So that is the mechanical power developed. So this much power is going to develop in the rotor, but the rotor is not simply an ideal person, right? It has some inertia, right? It has to rotate by overcoming the wind resistance as well as friction, right? So even though the mechanical power developed is PMD, there will be again another loss called the friction and windage loss in the rotor side, because the rotor has to rotate, the rotor has to move. Even though I developed certain energy, I have to rotate, means a portion of the energy will be utilized for that rotation, right? So a certain amount of energy will be utilized for rotation, that is called a friction, and windage loss will be there. So only after that minus these friction and windage loss will be shaft power or useful power. That is nothing but the turning power that we obtained in the motor. That is only the output power, correct? That is the output power. So this is the input power and this is the output power. This is the input power and this is the output power. That is the power flow diagram in induction motor. Very, very important. Draw it, my dears. Draw it. Clear? Can I have this? Next, induction motor. Next head is induction motor power stages or power relations. Induction motor power relations. We have, my dears, listen. Stator input power will be equal to, what is the input power equation? √3 into VL cos phi, correct? Where VL is the line voltage, line current, you know this. Cos phi 1 is nothing but, my dears, input power factor. Cos phi 1 is nothing but input power factor. So this is the input power. So from the input power, I already told you that there are some losses, right? There are some losses in the stator copper and stator iron loss will be there, and after that there is some air gap power, or I told you that the rotor input power, right? Rotor input power, which is represented by PG, which is, there is an equation for that you just mug up that equation. Okay, I2 dash square into R2 dash by S. I2 dash square into R2 dash by S. It can be simply observed by using that expression itself, no? That equivalent circuit, no? That equivalent circuit, see that equivalent circuit, approximate equivalent circuit. The rotor side input power is nothing but I2 square into R2 dash by S, correct or no? That is the total input power. That is the total input power to the rotor. And there is rotor copper loss happens, and which is equal to P rotor copper loss, correct? PCR. You may represent like PC copper losses, rotor copper loss PRC. Let be PRC, which is nothing but I2 dash square into R2. What is the difference between these two relations? See, in the air gap power there is divided by S, but in the rotor copper loss, because my dears, rotor copper loss is purely associated with the rotor resistance only. There will not be any what? S term. There will not be any S term. But here the air gap power, that power definitely contains some what? S term, because this power can be utilized for various things. That means this is the input power given to the rotor. That can be utilized for some type of rotor copper losses. Again, that can be utilized to develop the mechanical power in the rotor, because that power will continuously flowing, right? Because that power may contain a term containing the S, but purely the copper losses cannot contain any S term, because this copper losses is associated with R2 only. There is no terms associated with the R2 loss. That's all. That's all. Okay. That is actually it's a deep concept. You can definitely explain with that. This R2 dash by S can be again split by simply, I will tell you that. Okay. This R2 dash by S. or simply like I can tell you that R2 dash by explain this. See, elaborate this. Can I get the R2 dash? Let me check. R2 dash plus 1 by S into R2 dash minus R2 dash. Correct. See, correct. Okay. I will explain the term why it came. It's a deep concept, my dears. That's why I don't want to make you confused. That's why. See, this power is associated with this I2 square into R2 dash by S. You have a doubt there, why this R2 dash by S in the rotor input power PG and not in this copper loss, right? It is clear that from this copper loss is associated with the resistance only, so there will not be any slip term. But in the rotor input power, there is a slip term by, I will tell you. This R2 dash by S in the rotor equivalent circuit, in the equivalent circuit, I can split that R2 dash by S as simply R2 dash plus 1 minus S by S into R2 dash. If you solve, if you simplify this, you will definitely get R2 dash. Okay, which means this portion is responsible for rotor copper loss, and this is the terms which is responsible for rotor output. Rotor output. That means in R2 dash by S, there is a hidden term responsible for copper loss. There is another term which is responsible for the remaining power stages. The remaining power stage is nothing but the output power in the rotor. That is nothing but 1 minus S by S. So, if you introduce this 1 minus S by S into R2 dash, means there will be some S term. Of course, there will be some S term. Correct? So, that is the explanation. That means we reverse thinking. Think on reverse manner. R2 dash by S can be split by R2 dash plus R1 minus S by S into R2 dash. Only this way you can split now. So this is responsible for copper loss, and the remaining thing is responsible for the remaining stages of power in the power flow diagram bus. Correct. Okay. Is it clear, my dears? Is it clear? So that is the explanation. So you simply look up this. That is only sufficient, because no one will ask you how it came and why it came. No one will ask you. For your understanding, I told you. Okay. So the air gap power or rotor input power will be PG, and the rotor copper loss will be PRC. So definitely, my dear, what is PG by PRC? That is nothing but rotor air gap power divided by rotor copper loss. It is nothing but, or simply PRC by PG. That is very easy, no? What is PRC by PG? It will be equal to I2 dash square into R2 dash is dash medius R2 dash all divided by I2 dash square into R2 dash by S. Correct. So it will be simply S. This and this get cancelled, simply S. So PRC by PG will be equal to, my dears, S, or PRC will be equal to PG into S. Very, very, very important. Only you have to remember this, boss. You don't want to remember all this. Only you have to remember this. The rotor copper loss will be equal to S into the air gap power or the rotor input power. Okay. How much power you fed to the rotor? It is PG. How much power it is wasted as the rotor copper loss? It is nothing but S times the input power, bus. S times the input power is wasted as the rotor copper loss. Only you have to remember this equation, my dear. This is very, very important relation. In problems and all, it can be utilized. It can be utilized. So PRC will be equal to S into PG. That is very, very, very important relation. That's very, very important relation. Okay. Okay. So what will be mechanical power developed? What will be mechanical power developed? Can I remove this? Okay, I will here, right here. Okay, I will remove this. So what will be mechanical power developed, let be PMD is equal to mechanical power developed, let be PMD is equal to what, my dears? What is the mechanical power developed? Rotor input power PG minus rotor copper loss, correct? Rotor input power PG minus rotor copper loss will be the rotor mechanically developed power, not the shaft power, it is a developed power, correct? Is it correct? You are giving certain input to the rotor and a part will be wasted as rotor copper loss. So remaining will be developed power bus. So the input power minus rotor copper loss will be give you the mechanical power developed. Or simply it is equal to PG. What is PCR in terms of PG? It will be S into PG, my dears. So it will be PG into 1 minus S. Very, very important relation. Very, very important relation. PMD or the mechanical power developed will be equal to 1 minus S into PG. 1 minus S into PG. Okay. That is a mechanical power relation. Okay. Next, torques. Different torques, my dear. Different torques. We have a relation omega equal to simply 2 pi nt by 60. You know this relation, right? You know this relation. Then 60 into omega divided by 2 pi is equal to t. Correct? 60 into omega divided by 2 pi n will be equal to what, my dears? It will be a t, or it will be equal to, correct, it will be equal to simply t. Okay. Okay. Okay, simply you, so t is equal to 60 into omega divided by 2 pi n. Okay. Next. The air gap power PG can be write in terms of torque as 2 pi n into Tg divided by 60, correct? Now we are going to derive the torque equations in terms of powers. Okay, that's all. So PG will be equal to 2 pi n into Tg divided by 60, correct? We have the relation of omega equal to 2 pi nt by 60, correct? Omega is nothing but power. That means, okay, not omega minus, yes, there I stuck it. Clear. So power P is equal to 2 pi nt by 60. So 60 into P divided by 2 pi n is equal to T, or I can say that T will be equal to P divided by omega, correct? Because this can be right like P divided by 2 pi n by 60, no? This is also same, right? So P by 2 pi n by 60 is nothing but omega, because we have omega equal to what, my dears? 2 pi n by 60. Angular velocity is equal to 2 pi n by 60. So the P divided by 2 pi n 60 is equal to nothing but P divided by omega. So the relationship between torque and power is nothing but torque is equal to power by angular velocity bus. Torque is equal to what, my dears? Power by angular velocity bus. That is the relation. Okay, correct. So the developed mechanical, not the air gap power can be written in terms of the air gap torque as Pg is equal to 2 pi n into Tg by 60, or Tg will be equal to, my dears, 60 into Pg divided by 2 pi n, or it can be same as Pg divided by omega s. Suppose it is ns means it will be omega s, or I can say that Tg will be equal to Pg divided by omega s. Because T will be equal to P by omega is a general equation. Suppose you go for air gap power is nothing but it is dependent upon the stator supply frequency and stator speed, right? Stator speed in the sense stator magnetic field. Okay, so it will be equal to Pg divided by omega s bus. That is the connection between air gap power and the air gap torque. Okay, air gap torque. Next, you can see from here itself. And we have, my dears, we have n will be equal to 1 minus s into ns, correct? N is equal to 1 minus s into ns. This is the general equation for rotor speed, correct? We have omega will be equal to 2 pi n by 60 or omega is equal to 2 pi ns by 60. We have the relation, right? Omega equal to 2 pi n by 60. That means omega is directly proportional to ns, correct? So any equation which is apt for this n can be utilized for omega also, correct? So this is another important equation. You have n is equal to 1 minus s into ns. Similar manner you can write for angular velocity also. This is the RPM. You can go for angular velocity also, which is nothing but omega equal to 1 minus s into omega s, my dears. 1 minus s into omega s. Okay, so can we do something here? That is nothing but we have PMD is equal to what, my dears? 1 minus s into PG, correct? So what will be TMD? It is nothing but PMD divided by omega, correct? Torque will be equal to power by omega, no? Torque will be equal to power by, I can't write omega s here because it is the rotor connected. It is a rotor connected side, no? I can't say that it is omega s, it is simply omega. But PMD divided by, what is omega? Omega is nothing but, my dears, 1 minus s into omega s, correct? 1 minus s into omega s, correct? But PMD will be equal to what? PG into 1 minus s, no? So it will be equal to PG into 1 minus s by 1 minus s into omega s, correct? So this 1 minus s and 1 minus s cancel. So TMD can be right in terms of PG as it will be equal to PG by s. It will be equal to PG by omega s. It will be equal to PG by omega s, correct? PG by omega s. TMD can be either PMD by omega or in terms of PG, it can be PG by omega s plus PG by omega s plus PG by omega s. Okay, is it clear, my dears? Is it clear? Then what is the relationship between PRC by PMD? PRC is nothing but in terms of PG is S into PG divided by PMD is nothing but 1 minus S into PG, correct? PG and PG get cancelled, it will be 1 divided by 1 minus S. So PRC by PMD is equal to 1 divided by 1 minus S, my dears. Very, not 1, yes here. S divided by 1 minus S. PRC is nothing but what? Rotor copper loss. PMD is nothing but developed mechanical power. Developed mechanical power. So the relationship between PMD and PRC is that PRC by PMD is equal to S divided by 1 minus S. This relationship, no, you have to remember the equation because in problem a direct application will be there and you can directly substitute the value, you will get the answer. So please take care of these equations, okay? Take care of this equation. Clear? Next, approximate efficiency of induction motor. Efficiency of induction motor. Efficiency of equal to what is that? Rotor output by stator input, which is nothing but, my dears, 1 minus S. It's very, very useful relation. It is actually a derivation. After that only it will get, but we don't want that derivation. Simply you remember this. The efficiency of induction motor is in terms of slip is nothing but 1 minus S bus. 1 minus S will be the efficiency. Percentage efficiency will be equal to into 100 bus. Percentage efficiency will be equal to 1 minus S into 100 bus. So these equations you have to remember all the time. So in next class onward we will do some problems. Then it will be the when or how can we apply this equation, you will learn at that time. So now you just note down these equations. Definitely these boxed equations are very, very helpful in doing problems. Okay, so that's all for today, my dears. So we will learn more things on tomorrow, from tomorrow onwards. Bye.